Yes.
All right, so it's a pleasure today to introduce Minsung Kim. He's a final year PhD student in the Department of Computer Science at Princeton. His research interests include wireless networks and quantum computing. He received his BE in electrical engineering from Korea University, and he's the recipient of a large number of awards already. During his PhD, he worked as a summer intern at NASA for 2 years, InterDigital and Meta. And now he's going to tell us about warm-started quantum sphere decoding via reverse annealing for massive IoT connectivity.
Okay, thank you for the introduction. So this work is kind of like, this work was presented at ACM Mobicom conference held in Sydney, Australia last October. And I think you can think of this work as experimental study on reverse annealing conducted on D-Wave quantum annealers in the context of IoT connectivity. So during the first half of the talk, I'm going to introduce IoT networks and their properties and the motivation of this work. And the second half will more focus on quantum annealing, including the micro benchmark between the forward annealing and reverse annealing. Okay, let me get started. So with more and more device and application types, 5G wireless network identifies 3 different service categories depending on requirements. As you can see here, the IoT scenario, also known as 5G massive machine type communication, is one of them. And the IoT scenario has very different requirements compared to the others. And one of the most important requirements in IoT scenarios is to prolong IoT devices' batteries. And this is because in general, it's very difficult to replace their batteries. So for this, IoT devices are under sleep mode most of the time, and they wake up only when they have data to transmit. And another important feature in IoT networks is the number of IoT devices is increasing exponentially. And the main direction of the communication is from devices to base station, which is called uplink communications. So only a small portion of devices will become active simultaneously, but with the trend of exponentially increasing devices, internet connection for these massive devices need to be supported, and this is often called massive IoT connectivity. However, supporting massive IoT connectivity is not a simple task because resource block here consists of frequency and time resources. Single resource block can be assigned to a single device. And since frequency is very limited and expensive resources in wireless networks, and IoT devices do not want to wait long time because of the battery issue, so one of the main bottlenecks towards massive IoT connectivity is scarcity of wireless resources. Oh, by the way, I want to make this talk more interactive. So if you have any questions, yeah, feel free to interrupt me anytime. So in this regard, massive MIMO system can increase IoT connectivity using special multiplexing technique. MIMO stands for multiple input, multiple output. And here input denotes the number of devices, and output here denotes the number of antenna at the base station. So with special multiplexing, even single resource block can be assigned to multiple devices using parallel streams. So if I visualize this, so with MIMO spatial multiplexing, now we can utilize the spatial domain as an additional domain. So we can achieve the gains. So now we have more resources. It's easier to support the massive device count. So large spatial multiplexing gains are promising to support massive IoT connectivity. But however, for spatial multiplexing in MIMO system, the base station needs to demultiplex mutually interfering signal coming from the all users, all devices. And this signal processing technique is called MIMO detection, or multi-user detection, or multi-device detection. As the number of active devices increases, there is a big performance gap in MIMO detection between the theoretically optimal maximum likelihood detectors versus commonly used linear detectors. So ideally, the optimal ML detector is desirable, but the computation required for ML detection is increasing exponentially as device counts increase. So it's actually extremely difficult to enable ML detection for large spatial multiplexing gains. To resolve this issue, there have been a lot of lines of research. The last one is kind of relatively recent one, is quantum and quantum-inspired algorithm to accelerate ML processing using the specialized hardware. And in this work, I'm going to introduce IoT-ResQ, and this one utilizes the reverse quantum annealing to accelerate ML processing for massive IoT connectivity. And IoT use both classical and quantum-based detectors together in a synergistic way, and its structure is a sequential classical quantum hybrid approach. Let me first introduce the envisioned scenario. So a lot of base stations will be connected through optical fiber cables to the centralized baseband unit pool. And most of the computation will be done in the centralized part. And this structure or architecture is called CRAN architecture, centralized radio access networks. And this architecture is very promising for many practical reasons. And as it's CRAN architecture, the only assumption we're going to have for this work is quantum processing unit will be co-located at the centralized baseband pool. In our work, we made use of quantum D-Wave advanced system as QPU. So contents will be like this. So in primary section, I'm going to introduce background knowledge to understand this work. And second, I will explain IoT-ResQ structures and algorithm we use. And last is the evaluation of the system. So let me explain what multi-device detection is in MIMO spatial multiplexing. So in MIMO spatial multiplexing, multiple devices will send signal to the base station simultaneously, and each wireless symbol, they're all together can be expressed as a symbol vector V. And they go through the wireless channel, and the channel can be expressed as a matrix. So if you assume n devices at the transmitter side, and if you assume n the same number of the antennas at the base station, this channel matrix will be n by n. And what actually base station received is the transmitted symbol vector multiplied by H matrix and perturbed by noise vector. And the problem is we don't know each component. But thankfully, through the pilot symbols, we can estimate wireless channel H. We're going to assume this H is exactly the same as this H. And in this case, what detection is signal processing to estimate transmitted symbol vector V at the base station based on received signal and estimate channel, wireless channel. And let me introduce the optimal method for this. Sphere decoding is an efficient way of ML detection. But let me introduce the optimal maximum likelihood detection first. And this is the formulation for ML detection. So it's basically checking all possibilities in symbol combination. So they're trying to find the symbol vector that leads to the minimum value of this objective function. So in order to utilize sphere decoding algorithm, the first thing we need to do is we need to transform this ML detection into equivalent tree search. So how can we do that? So
Minsung, can I ask a question here?
Sure.
So this problem right now seems classically very easy, unless you are assuming that there's some kind of discretization of the vectors and matrices involved.
This is not. So you're talking about the detection itself or ML detection?
The problem on the next slide, which is to find V. Yeah.
Oh, this is not simple because Y is known information, H is known, but we don't know the V. So we need to check all possibilities. So for example, modulation size is 4 and there are 100 devices. That means we need to check 4 power 100 possibilities to find the global optimum.
Yeah, but so isn't this just a quadratic optimization problem over real over real vector spaces?
It's a complex values, the complex vector, but still the complexity of the problem increasing exponentially with the size of modulation and device count.
So okay, let me ask it this way: isn't this a convex problem?
It's not convex; it's NP-hard problem.
Oh, okay. That's why I'm misunderstanding something then.
Yeah.
What makes this not convex and NP-hard?
What makes because the possible, search space is increasing exponentially based on the modulation size and number of devices. I think I can make it more clear this in the next slide.
Okay.
Okay, let me continue. So in order to make use of sphere decoding, the first thing we need to do is we need to transform this ML detection into equivalent tree search. And the way for that is we applied QR decomposition to this H channel matrix, and then we multiply Q Hermitian transpose in the objective function. Then, based on the definition of orthonormal matrix, what we'll get is this form. Here, the blue part and these blue parts are known information. So this to decide the solution candidate, what we can do is, so once we decide V1, and the decision of V1 will affect V2, and decision of V3, decision of V1 will affect decision of V2, and decision of V3 will be affected by V1 and V2's decision. So this can be expressed as a tree search. Am I clear about this?
Yes.
Okay, thank you. So let me move on. And this is an example of decision tree. So in this case, I assume 2 devices with QPSK modulation. QPSK modulation means there are 4 possible wireless symbol per device. So each IoT device will send one of this symbol for communication. And of course, these are 2 devices situations. So possibilities 4 power 2, 4 square, so 16. Before I explain sphere decoding, let me explain how brute force ML detection works. So brute force ML detection is checking all possibilities, symbol combinations, and then they choose the best one. So here, this 5 is a cumulative metric based on this path, and there is a branch metric, and this branch metric is non-negative, and so this branch metric is 4, and this branch metric is 1, and this one is a cumulative value. So among all the leaf node metric, this one is the minimum. So this one will be the final answer of the ML detection. So this is equivalent to, given search space, we check all possibilities and find the solution that corresponding to the global optimum. So, and this leaf nodes value are often called the Euclidean distance. Okay, now let me explain the spirit decoding algorithm. So spirit decoding is an efficient way of ML detection with reduced complexity. So the first spirit decoding explore the first device's symbol possibilities. So there are 4, and the spirit decoding picks 1, and then explores the device 2's symbol. And among them, this one is the minimum. So our goal is to find the global minimum. So now we can ignore the others. And this one will be our solution candidate. And this one will act as a constraint for pruning. So let me clarify this. So now, this one's metric is already 9. And as I mentioned before, branch metric is non-negative. What I mean by that is any metrics, the metric values in this leaf node will be bigger than 9. That means like all nodes here will have values bigger than 8. So now we can safely prune that tree. So by doing this, we don't need to visit all the possibilities. And then it explored this symbol, and now we find a better solution. Now we update it, and then we move on. And at the end, we will find the best one. Then we'll choose this one as a final solution. So this is a spirit decoding. And this spirit decoding has reduced complexity compared to brute force, but it has a problem. It has problems, actually. So first of all, based on its sequential structure, it has varying complexity for instance. So precisely, depending on instance, we don't know how many nodes will be pruned by this algorithm. So that's not actually, this is actually a very serious problem in terms of the hardware implementation, because we cannot make use of parallel processing, and also we cannot, so that there is a synchronization issues for this algorithm. So fixed complexity spirit decoder, or FSD, was introduced to resolve this issue. So in FSD tree search, first it applies a full search for first devices, and then it applies greedy search from the given level. So, and then we have 4 candidates here, and among them we filtered the best one as a solution. And this processing structure is parallelizable easily, and it has a fixed complexity because it always visits the same number of nodes. The problem is because of the greedy search part, now the algorithm becomes approximate. So if the wrong decision in the middle or early stage of the exploration, then it will lead to a suboptimal solution. So in this case, device 2's decision was wrong. So at the end, we'll get the non-optimal solution. So this is the FSD algorithm. Now we are ready to talk about IoT-ResQ system. Do you have any questions so far?
Yeah, so in the examples that you just described, you used integer values. Was that an accident, or is that really what's going on in these problems?
It's not integer at all. So I just used a toy example, just to clarify the algorithms. So it's like real values, has to be real values, because it's norm scale values. Yeah.
So I guess I'm still a little confused about what makes this problem NP hard, except for the exponential dimensionality of the search space that you were.
Yeah, the problem is we are targeting over like hundreds of devices. So that means, like in this case, 4 power 100 is our search space, and we need to check every possibilities. Then the complexity, I mean, the wireless network is a real-time system. So we have limited processing time available, up to like 3 milliseconds. So like we cannot enable ML detection, under that time constraint. So that's the problem of.
Okay, so is the issue that you have this quadratic optimization problem with a time constraint?
Yeah, time constraint. Yeah, up to like, so detection needs to be done within like hundreds of microseconds, and that's a very critical part in this work.
Okay.
May I ask you a question?
Sure, sure.
Is this a process that is actually used in practice?
In practice, actually, in practice, much more simpler. Okay, let me just want to. So in practice, actually, much more simpler processing methods are applied. But problem is, so problem is like their performance are very poor for massive IoT connectivity, more precisely large multiplexing gains. So for example, jetforcing, let me explain jetforcing a little bit more. Let me go back to this one. So what jetforcing does for MIMO detection is we have received signal and we just apply inverse of channel metrics. Then assuming we have inverse channel metrics here, then this channel will be canceled out, right? And noise will be H inverse multiplied by noise vector, right? But problem is, in the case of the large MIMO special multiplexing case, the channel condition is bad and it can amplify the noise. So the performance becomes pretty poor. So when the active device count is small, then they work well like this. So this is this scenario assume 176 base station antennas. And when a device count is like around 45 or less than 60, they work well. But as device count increases, then their performance becomes very poor, while optimal solver still has very good performance. So,
but this zero forcing detector is used in practice because it's fast.
It's fast. So, but we need to assume small special multiplexing gains, but that's not the case in the case of the IoT scenarios.
I understand.
Okay. So far I introduced the IoT networks and problem of our interest, and now let's move on to our system. So IoT-ResQ. So let me first introduce quantum annealing. I think most of the potential audience of this talk through this channel must be familiar with quantum annealing, but let me explain very high level description. So quantum annealing is an analog computation algorithm, and in the case of D-wave quantum annealer, qubits are implemented on superconducting circuit. And quantum annealing is an Ising solver, so its input form is Ising form, and Ising form is just the minimization form whose objective function consists of linear and quadratic terms, and coefficients are real values, and the variables are binary, either -1 or +1. And these coefficients will be decided by our problem of interest, and the values of this objective function are called Ising energies. So the goal of Ising form is to find the ground state that leads to the minimum Ising energy among all possible spin configuration possibilities. And quantum annealing is probabilistic heuristic method to solve this optimization form. And output per anneal is the solution candidate. So since this is a probabilistic technique, so one run entails multiple anneal cycles, and we collect the sample, we collect the solution candidates, and we filter the best one at the end as a final solution. And compute time can be expressed as the anneal duration multiplied by anneal count, and anneal count is controllable. So in the case of our implementation, anneal duration is around 2 microseconds. And now So Ising form is the input form of quantum annealing. So the first step we need to do to accelerate ML detection using quantum annealing is to transform our problem of interest into the equivalent Ising form. And this is quite simple. When we so any linear wireless symbol to spin variable transformation can lead to Ising form. So every possible spin configuration possibility corresponds to possible symbol combinations. So these two are exactly equivalent, and the ground state of Ising form is always equivalent to ML solution in ML detection. And in Ising forms, there is no constraint terms at all. And I believe this is atypical. So what I can say about this is these two are exactly equivalent without requiring any penalty terms or something. Okay.
May I ask you a question?
Sure.
On this, right? This can be transformed to the left-hand side equation can be transformed to the right-hand side because V is a discrete variable.
V is complex, but yeah, it's a discrete. So
Okay.
V is like something like this. So this symbol 1 plus 1j, this one is 1 minus j, something like this. So we can express with spin variables.
Okay. Fine, thank you.
Okay. So let me introduce how IoT-ResQ operates. So when base station receives the wireless signal and it estimates the channel metrics, then we transform ML detection problem into Ising form, and then we embed or program that Ising form onto quantum hardware. And after that, we're going to apply reverse annealing. So reverse annealing is a variation of quantum annealing where computation starts from a programmable classical state. So if I clarify this, so we first program an initial state, and then we introduce quantum fluctuations, and then we'll get the final solution at the end. So for this operation, we require the initial state. For that, we make use of FSD solution I explained before. So, and as you can see here, the reverse annealing naturally provides an opportunity of hybridization, and this hybridization operation can boost quantum optimization performance. And let me explain this. So quantum annealing algorithm in IoT-ResQ is reverse annealing, and I'm going to explain reverse annealing comparing against the standard forward annealing. So let me explain forward annealing first, which is the baseline algorithm in this work. And the system called QAMX, introduced in SICOM 19, made use of this standard forward annealing algorithm. So annealing algorithm can be defined as annealing schedule, how to transform the state of the problem. So from the fully quantum state to the fully classical state. So forward annealing starts its computation from fully quantum state. And that means we're going to prepare the quantum superposition state, where every possible states will be held in this one state. And then it goes to the classical state, except that we introduce pause in the middle because pause can improve the overall optimization performance. And it goes to the fully classical state. And meanwhile, quantum search is applied. And at the end, if we measure this the state, then we'll get the one final classical state as a solution. And in ideal cases, the final state will be the ground state. In the case of reverse annealing, the algorithm applied in this work It starts its computation from fully classical state. And this fully classical state does not require a very low temperature for operation. So this algorithm often called the warm-started quantum annealing. So from a classical state, let's assume this is our initial classical state. It goes back to our quantum state. And this quantum state is still holding the initial classical state. And then we introduce pause for the same reason. And then it goes to the final classical state. So then, meanwhile, quantum search operation tends to be acting like refined local search around the initial classical state. And this can improve the overall optimization performance because on actual quantum hardware, we can utilize only limited quantum fluctuation due to quantum decoherence and quantum noise. So when search space is pretty large, we simply apply quantum fluctuations to the all such space, often fail to find the global optimum. But in the case of reverse annealing, so instead of merely applying quantum fluctuations to all search space, we give the initial good solution candidate. And then by limiting quantum fluctuation only around the initial state, it can improve the optimization performance, and it's better to find the global optimum. So yeah, do you have any questions so far? I think you guys are familiar with this. If I visualize this search operation as an overview, so this is the QAMX and this is IoT-ResQ. This is the system we present, and the upper line is tree search view, and the lower line is equivalent quantum search view. So in the case of QAMX, I simply apply forward annealing to the search space. So it doesn't do anything and just simply apply forward annealing. But in the case of reverse annealing, in the case of IoT-ResQ, I didn't like detail explain this the full search in the IoT system. No, so in our system, but it applies FSD as an initial solver. So we have multiple solution candidates, and since we decompose the original search space, now we have smaller sub-problems, and then we apply reverse annealing to each of them in parallel. So reverse annealing acting like this, and here this sub-problem entails the global optimum. So this is the FSD candidate, one of the FSD candidates, and apply reverse annealing. So hopefully it moves to be a global optimum. And this is the overall system comparison. Okay. So now let's talk about evaluation. And let me start with micro benchmark on comparison between forward annealing versus reverse annealing. And for micro benchmark purpose, I used time to ML, also known as time to solution, as metric. So this metric represents required compute time to obtain the global optimum or near optimal performance with target confidence. So the lower, the better. And this red line is the median performance of forward annealing for different instances. Here, each symbol represents each instance. And as you can see here, at some point, forward annealing fails to find the global optimum. And now, let's see the result of the reverse annealing. So in this case, we assume oracle knowledge. So we applied reverse annealing to the initial state that has only one Hamming distance against the ground state. So as you can see here, the reverse annealing performs much better than forward annealing. And this is the reverse annealing from initial state that has Hamming distance 2, and this is 3. And
a quick question here.
Sure.
So do you know the ground truth solution?
No, of course not. So here we just assume the oracle knowledge. but this is just for micro benchmark purpose.
You assume what?
Oracle knowledge, so it knows everything. It's just a test problem, so we know the global optimum in this case. But in actual wireless system scenarios, of course, we don't know the ground state.
Yeah, okay, no, but if for this benchmark, you do know the ground state.
Yeah. So benchmark we do.
Okay.
So some might think that this Hamming distance is too small compared to the variable count. So in this case, we assume QPSK modulation. So spin variable required for this scenario is exactly same as the device count here. So in this case, this is the 128 spin Ising form, the logical spin. So if we keep increasing the Hamming distance, initialization Hamming distance like this, and interestingly, up to nearly the half of the variable count, reverse annealing outperforms forward annealing here. I think this is very interesting observation. And this active count here actually can represent over hundreds of thousands deployed IoT device scenarios. So it's actually has some potential to support massive IoT connectivity. And the message I want to deliver here is RA reverse annealing can outperform forward annealing when initialization states have the low enough Hamming distance against the ground state. But in practice, we actually don't know the ground state. So my next question is how well classical solvers, classical detectors can satisfy these conditions. So I'll show that one. So this is the cumulative distributed function of the Hamming distance obtained from classical detectors. So we test zero forcing, which is simple linear method, and FSD is our initial detector we used. And as you can see here, actually the Hamming distance is not that bad because this is a 160 devices scenario. So it means 160 spin variable will be there. That means the half of the spin variable count is 80. So it's as you can see here, the CDF converts to the 1 around like 20 in the case of FSD. So FSD is the good initial solver. And if you increase the base station count, base station antenna counts, then this we can improve the quality of initial state in terms of Hamming distance dramatically. So Hamming distance achieved from conventional classical detectors is low enough for RA to outperform forward annealing, and this is our observation. And thanks to this, now we can show the performance of reverse annealing in terms of bit error rate performance. And this is the fundamental metric to evaluate MIMO detectors. So, so in the case of quantum annealing-based detectors, we can control the compute time based on the anneal counts we use. So if we plot the bit error rate performance of QAMX, which is based on forward annealing, it actually performs worse than the other conventional methods. But in the case of IoT-ResQ, which is initialized from the FSD solution, so it starts its computation from here, it rapidly converts to the global optimum. And here, of course, we assume the Oracle scheme. So we assume we know the global optimum in this case. And so
may I ask you a question?
Sure. What's
the overhead of classical initialization?
Overheads. That's an interesting question. So, as you can see here, zero forcing and MMSC is very fast solver, and this is actually their compute time is less than this because this assumes the worst case. And FSD takes a little bit longer time that, and the overheads we should consider is programming time on QPU. So we need to do embedding, and also there are a lot of overheads in quantum annealers. So actually, the actual compute time is very far from these values. But this is we assume the best case without overheads here.
Okay, I asked the overhead in the part of the classical.
Part of classical. So in the case of FSD, it's a parallel processing, right? So it needs to merge all solutions because we will get multiple solution candidates, and we need to find the best one among them by filtering, right? So there, in that place, overheads will be cost. And other thing is we need to do QR decomposition, and QR decomposition is not required in linear methods. So that's another overheads. And I think, I can think of those two right now, but there must be a lot of like overheads we should consider for this kind of like sequential structure.
Okay, I ask this question because even with those overheads, both classical and quantum, the reverse quantum annealing method is still competitive against conventional classical methods. That was my question.
Yeah, so this one is just this study actually trying to show the feasibility of this kind of hybrid structure, but it's actually very far from the practical designs, at least with these current levels of maturity of technology. But like we want to take some long-term view for this kind of work. Hopefully there will be less overheads, and maybe customized hardware and customized devices can reduce this kind of overheads like significantly. And that's our prediction on quantum annealers and the future quantum devices.
Okay, you have a longer view than me.
Yeah. And all good news is, in IoT scenarios, actually, maybe longer computing time will be allowed, because IoT is not that latency sensitive application in general compared to mobile like standard mobile communications or what else, URLLC, like ultra low latency. So I introduced 3 different categories, and as you can see here, latency is not very high priority for IoT case compared to the others. So maybe a little bit longer compute time will be allowed in IoT scenarios. That means maybe there is a chance of accepting those kind of overheads.
Okay, I understand. Okay, thank you.
Okay. So what's happening here, if I visualize this, what's happening here is we get FSD solution, and based on the FSD solution, we applied reverse annealing, and FSD algorithm is approximate algorithm. So the solutions are often not the ground state. So we hope reverse annealing can move the non-optimal solution towards the optimal solution like this. And since now we can control the reverse annealing compute time, we suggest the pipeline design. So this is a classical quantum sequential structure. So if we assign exactly same amount of time we need for a classical part to the quantum part, actually we can enable this kind of pipeline design. So, but as I mentioned before, if you consider overhead, this is not possible. So in our implementation, we implement this completely disjoint stage. But like, this is the long-term view for sequential, classical, and quantum hybrid design. So now if we present the bit array performance at the pipeline points, as you can see here, IoT-ResQ can outperform both conventional classical detectors and fully quantum detectors, which is Quantex here. And IoT-ResQ was able to enable some currently challenging the IoT scenarios where all the other detectors fail to report poor performance. And this is actually the last page, but I have some interesting results I want to share in my appendix. So I want to talk about the initial state quality for reverse annealing. So in our work, low Hamming distance against the ground state is a good initial candidate initialization state for reverse annealing. But some might say, isn't it more related to Ising energies of the initial state? So interestingly, this is the QPSK modulation. X-axis is a search space, and y-axis is Ising energy or cost. So we observe some correlation between Hamming distance and Ising energies here. So this is the sorted solution sorted by solution rank sorted by Ising energies. So the rank 1 is global optimum ground state, and the high rank solution has only one Hamming distance. And there's as you can see here, there is some correlation. But in the case of high order modulation, which is not used in IoT scenarios, we couldn't observe any correlation, high correlation at least. So actually, in the case of high order modulation, it's very hard to decide initial state. But another interesting message I want to deliver here is Ising energy. So Ising energy that are close to global optimum are actually might not be the best initialization state. So let me explain this. Okay. So this is the reverse annealing's time to solution performance. And we initialize from the state that has only one Hamming distance. So this is a 16 variable scenario. So there are 16 possible initial states in this case that has only one Hamming distance. So this one, so x-axis is corresponding Ising energies, and this is sorted by Ising energies. So according to our assumption, so the lower Ising energy will lead to better optimization performance. This one has to lead the best performance of the time to solution. So this is the global optimum value. So this is the ground state's Ising energy, and this is the very close initialization state, right? So this one must be initialized from somewhere around here. And interestingly, the performance are worse. The time solutions are worse than the initialization state that has lowest Ising energy. So I believe this is very interesting finding. Actually, these figures are not in our paper, and now I'm working on this work and prepare for publication. But I think this is interesting result I want to share. So my conclusion about reverse annealing is we still don't know about the best quality or good quality of initialization state. So in conclusion, in this work, we studied the feasibility of classical quantum hybrid computing in the context of the massive IoT scenarios. And we explored the warm-started quantum reverse annealing, which is a sequential classical quantum structure. And we introduced the micro benchmark between the forward annealing and reverse annealing. And we empirically shown that the reverse annealing can boost the optimization performance by mitigating some quantum decoherence and quantum noise. And interestingly, this IoT-ResQ design can be synergistically applied with other emerging IoT technologies, such as NOMA or grant-free access, because whatever situation it is, the always ML detection is the theoretically optimal. So it's the performance is desirable. So our future work will focus on enabling high order modulations. High order modulations are not used in IoT scenarios, but But in the case of EMBB or URLLC, the other categories than IoT scenario needs high order modulation. So this is the fundamental challenge left in the in this direction. And yeah, thank you for listening to my talk today.
Great, thank you very much. That was very interesting. So one follow-up question I have is, so you did this micro benchmark of forward versus reverse annealing, but a natural question that always comes up in any kind of a benchmark of quantum annealing is what happens when you if you replace the quantum annealer with a classical simulated annealer. Have you tried that? And do you know if you still get better performance than, or is the quantum performance better than classical performance? So QAMX is based on forward annealing, and IoT-ResQ is based on reverse annealing, and ParaMax is based on simulate annealing with parallel tempering. So in terms of the probability of finding the global optimum, ParaMax is the best for these scenarios. But in the case of ParaMax, each anneal duration keeps increasing, as the problem size increases. But in the case of quantum annealing-based solvers, anneal duration can be fixed. So when we plot the time to solution TTS performance here, actually, some scenarios, the parallel tempering works worse than quantum-based solvers. But of course, this is like we didn't care about the overheads, but yeah, at least based on pure computation, this is what we observe. Okay. But yeah, in terms of sampling quality, parallel tempering is best one so far.
May I ask you another question? Sure. In reverse annealing, you fix the reversing time. That is, you decrease S from 1 to some intermediate value and pause the process for a while and for the process to S1 once again. So the reverse annealing timing, that is S, which we often call S star, which is the time that you fix the process for a while, should affect the performance in many cases. Sure, of course. Have you tried various values?
Yeah, so in our previous work, so this work was presented at HANNEX workshop, and we tried different pause and switch location, and we find the best one by the brute force methods. So we check every possible and put location, and we find the best one, the best average performance. And we did similar thing, for the forward annealing too. Yeah, like this.
So the result depends upon the pausing location significantly or not very much.
That's an interesting question. So so in the case of forward annealing, so this is the pausing location study. So we fix the pausing location in the case of forward annealing around 0.3, and after that we ignore the effect, the impact of pausing location. But I would say once we find the proper value, I don't think it will lead to very serious performance gap. And as I believe this is the case for reverse annealing as well, because
okay, I ask this question because in practice, you don't have time to grid search the best place to pause.
So for that, we just do some pre-study, like we just check small number of instances with brute force, and we just pick proper, not bad, like proper best average parameter for that one. And after that, we forget about tuning that parameter at all.
Yeah, that's reasonable. Thank you.
Okay. Toshi, did you have any more questions?
Well, I don't think so.
Okay. All right. Well, then, thank you very much for an interesting presentation. And we'll conclude the talk here and encourage people to watch it online.
Thank you.
Thanks again.
Thank you.
Okay, bye-bye.
Okay, bye.